I will try to briefly explain again in a very easy graphical explanation that I just explained you in the break. I think it's quite good to understand more easily what are we doing and the reasons to stop our iteration, our clean algorithm. So let's imagine that we have several sources in our field. Like we have a very strong point source. Next to it we have what Gaussian-like, if you want. We have like another weak one. And let's assume we also have an extended source like this. Okay, this is sky brightness and this is spatial coordinates. You can think of making a slice to your clean image. Okay, so we start our clean algorithm. We have two parameters that control the algorithm. We have number of iterations and threshold. Okay? And the question is, how do we decide what to put in there? Okay? I already mentioned that when you observe with a radio interferometer, you have a theoretical limit on the noise that you are going to get, depending on the observing time, the number of antennas you have. So this would be our image, but then we will have here our noise. Okay, perhaps? I don't know if... Okay? And this, you can get it already beforehand from the website of the telescope, or if you use a formula, you have your RMS. Perhaps this is already 3 times. Okay? This is the noise in your image. So we start our cleaning process. So what do we do first? We look for the brightest point in our dirty image. Our brightest point is here. Okay? So I'm going to take a point source, convolve it with the Gaussian smooth version of my beam, and subtract it from here. I will not subtract it completely because I have the gain. If the gain is 0.1, I'm going to subtract only 90% of my source. Yeah, 90%. So I feed my point source here. Okay, I feed it. And then I subtract it from the image. I don't subtract it completely. There is something left still, but it's gone. And I save it. In number of iteration 1, I have one clean component, the brightest one, and I save it for the clean image. Okay? Now I go back to the dirty image and I look for the second brightest point. So the second brightest point is here, and I do the same exercise. I fit a point source, right? And I subtract it, not completely, but almost gone, and something is left there. Okay? So now I have number of iteration 2 cleaning components that I will save for my image. I go back to the image, I do the same. This one disappears. I save it. So now my clean image consists only of 3 point sources. Okay? And this would be my residual. I could decide to stop here. Why not? But perhaps there is a quantitative way to decide when to stop. So one of the criteria to stop is to decide, okay, I'm going to stop cleaning until I reach my noise. Because then, I mean, it doesn't make any sense to be cleaning point sources at the noise level. This is not providing me of any scientific information that I'm interested in. So then I could try to put a threshold of, for instance, 2 times the RMS. Okay? I would keep cleaning and saving components until the next brightest peak is already 2 times the RMS, and then I stop. For that, I would choose, if you are going to raise your criteria in the noise, I'm going to put a very, sorry, it's an eater. A huge number of iterations, I don't care. I don't want to be stopped by the number of cleaning components. I want to be stopped by the threshold. I would do 2 times the RMS. Okay, so then my algorithm will keep looping until the residuals are as bright as the 2 times the RMS. And then I stop. But I could also, my goal may not be just to reach the RMS, but I would be happy to explain my source with the less possible number of components. And what I really want is a contrast, a good contrast in my image. So for that we use what we call the dynamic range. So some of you already mentioned that you are familiar with this. And if you So the dynamic range is basically the ratio in between the brightest point in your image with respect to the peak in your off-source image. So the peak of the brightest point and the noisy area. Okay. And let's say you want a high contrast of 100, 100 times a brightest point with respect to the off-source area. So then, in that case, I would put a threshold of 0, and I would put a low number of iterations, 40, 100, whatever. I would do 40 iterations. So let's say I'm now, in this case, I haven't stopped yet, I have 3. But then I reach this target here, this component. This is an extended source, and I'm trying to explain it with point sources. So I'm going to search for the brightest point here. Let's say it's here. And I'm going to try to fit a point source and subtract it. Okay. But this is not gone yet. So in iteration number 4, I had 4 cleaning components, but I almost did nothing to that. I go again, I fit another point source, I subtract it. It's almost making nothing, right? So then I have like 5 cleaning components. In order to clean all this source, perhaps I need 150 cleaning components. Okay? So then I managed to clean it, but perhaps the residuals are a bit higher than my RMS. But if I compare the peak of my clean image with the peak and the residual, perhaps I'm already happy and I can stop. So I can stop already in the iteration 150, and I don't need to go further because I already have enough contrast. So this is the other way to stop your cleaning process. So I hope this way you could see much better that cleaning an extended source with point sources is going to add you a lot of iterations and a lot of cleaning components. So perhaps your goal is to try to explain your source with a very simple model that you will use later for fitting whatever you need, and you like to explain it just with 3, 4 point sources at most, and you don't care if there is extended emission there that you are not going to model anyway, why you will be cleaning until the noise. You can stop much earlier. So what you do usually is just to put a low number of iterations, and then when you stop, you compare the peak of the clean image with the residual, and then you decide whether you are already happy. If you are not happy, then you can tell the algorithm to start again. I don't think in AbsynSim you can do that, but the cleaning algorithm doesn't need to start from 0 again. You can tell it start from iteration 100 and go until 200, and then you check again. You don't need to, okay, go back and start from 0. So you put a slow number, you check, you may want to do more iterations, you keep going, and then, yeah, because you put a threshold of 0, the reason to stop will be the number of iterations that you have set. So I hope this is...
What is a good value for the threshold?
Yeah, for a threshold, 2 times the RMS, yeah, there in the AbsynSim, I don't know how you can put an RMS, because you cannot do statistics either, I think.
2 times the RMS?
Yes. Yeah, you can do. Yes. What you need to do, I think I also have put it in the slides, you can do it later. If you are willing to stop this way, what you do when you have your clean image is that you go off source. You have your bright source here, another extended source. This is your image. You go to a region here, and then you measure the RMS. And ideally, if you have done things right, it should be a Gaussian with the expected RMS that you... If you have not cleaned well, or you have stopped before, you will have a tail, right? You will have a tail of the components that you haven't cleaned yet. So if you are willing to clean up to the RMS, once you finish, you check that your RMS of source, it's consistent with the expectations. It's Gaussian and it's random noise, basically. Yeah, here, I don't think in AbsynSim you can get up an estimate of what's the RMS beforehand. But yeah, I think you can play by putting different, if you are stopped by putting a low iteration number, or if you are stopped by putting high iteration number, or whatever number comes here. To have an idea on what value you put there in AbsynSim, I think you can go, like in the residual or in the final image, you can go off source and put the mouse there to see what's the level of flux. And you could use that as a first, as a guess for this threshold. And this way you can just set up the parameters and let it go, and you don't have to monitor. Okay, I think, yeah, the gain. You can, yeah, depending on how confident you are on how the image look like, if it's really only point sources, then you can perhaps put this value a bit higher, sorry, lower. You can extract already the full point source at once. But if there are extended sources around, you may want to be conservative in the amount of flux that you are subtracting at every step. So, yeah, I think.
Also, when you subtract the lesser bright points first.
How will you find the lesser bright point? Like the most negative one, or in absolute value, you would? I guess there is, but nobody uses that. Why would you? Why would you do?
For me, it looks that there's more useful information in the lesser breakpoints than in the brightest.
So you would like to start fitting the negatives. What is the value there? What are, if you point with them? It's negative?
I don't know, let's see.
If you click, I think if you click it should give you, yes. If you click also on the red, it should give you how percentage this is. You would like to start cleaning. Yeah, you can do that, but it's not going to be. You are willing to start cleaning out the most negative one. I guess you can do that, but why do you? So negative sources. What do they really mean for you?
Maybe disperse cloud gases.
Diffuse clouds
Diffuse clouds.
with a negative flux.
Yeah. Or maybe the array wasn't good enough. Like in this image, I want to take the eye, but I got the brightest point not in the eye.
Yeah, because in this case the eye is not a source. There is nothing there.
A diffuse cloud.
Negative.
I don't know if that's my
No.
question. It can be done. There's a sense for it.
Oh yeah, you could do it if you wish. You can invert your pixel value. Why not? You can make the absolute value of this if you want, but yeah, if you wanted to for you to consider that the eye is the source of interest for you, not because it's negative, it's because in your brain you are thinking that, then you can do the negative. Yeah, so you can invert that, and then it will, no, because we are not. So the negatives in the dirty image, they are not sources convolved. So they are the side lobes of the model convolved with the sampling and of the PSF. Yes. So because you have your sampling has a response, your source is positive. Is something with positive flux, and when it's convolved with this, with the best PSF, then is when you get the holes, the negatives in your image. But in principle, a negative source with negative flux is not something that you. Well, it's just not there. If you want to relate the flux to a mass of H1, for instance, a mass of gas, if it's negative flux, it's not. It's a negative. I know what you mean. You are trying to perhaps to talk about how to detect absorption, but this you don't get this by cleaning the negatives of an image. The absorption is measured when you have different measurements for different frequencies in your source. You have your source.
Now I understand.
You have your source, and it has a continuum. In most of the frequencies, has a continuum flux, more or less. Or it can, depending on the kind of source, it can can have something like that. Sorry, like this, or it can be depending. But let's assume it's a constant source point continuum. What you will see is that you measure the flux of the source in the same area, and then in certain channels you miss it. Right? And this is the absorption. You have the source, and because you are observing something bright, and there is something in between the source and us, it's absorbing in certain frequencies. But you will not see, it's not a negative in your continuum, if this is what you were meaning.
Yeah, thanks.
Okay. Sorry, I guess they all know what to do, and yeah, so I assume you all are playing already. You have the slides and you are already doing the exercises. I wrote 3 exercises, and I will ask you to upload to the website only the part that is written in red. So then it's up to you if you want to play with the rest, or if you need the other steps to reach there. But yeah, I will put the red parts to be uploaded to the website. Okay.
Can we choose the value of any of these things without using the
I
mouse?
know. Yeah, I know it's quite. I thought about that myself, but
You
I
can?
don't know. I don't know how. I'm sure because it's a Python script. I'm sure it's reading it from there, but
Yes.
I know what you mean. Yeah, because it tells you put that value.
Exactly.
If it's not exact,
It's okay?
it's okay. It's more a qualitative difference. You are not going to make a. Yeah, because I also try like if there is a way to put all the parameters and fix by writing them instead of moving the bars.
Yes. Okay.
Yeah, I don't know.
It's okay.
I'll try to. Actually, what I will be doing is I'm writing down things that I find myself or that people comment, and I will send them to Ivan to tell him it would be nice if you can change the number of pixels, put in these things, and also because the software, as it is right now, it's not reading the latest configuration files of Alma. So, by the way, it's written, but perhaps if he modifies the software, then they will come and be reading. asked me what was a gray, right?
Yeah.
And what was it?
A Fourier
the sum.
transform or of something, I don't know.
Okay, I will, yeah.
Here it says, observe the 5 Gauss model. I have the 5 Gauss model with the 2 antennas array. I have it now.
Okay.
At 1 millimeter.
Half
the
an hour,
wavelength.
yeah. Yes.
Yeah, okay.
It's a bit tricky. It's a bit tricky to get the exact wavelength, just because you need to move it with the mouse. So what I was trying to figure out is, yeah, that's okay. You don't need to.
Yeah, but my question is, I got this, and that's what I'm being asking.
Yes. So that's
one of the source components around it. They say mask.
Yes. Okay. I'm going to do it myself because I didn't explain the cleaning boxes. You have, what is the
I don't know how.
the put it reset? Yes. So I did.
But the residuals changed because I changed the wavelength.
Yes, of course, but it's the dirty image is the one that you have, right?
Yeah.
I'm going to explain it now, but what you make with the mouse is a box in one of the sources, and you are basically telling the algorithm only subtract point sources signal from here.
Okay, thanks.
The rest, I think, so because you are an astronomer, you are super clever, and you know, whatever. Then by giving small boxes or big boxes to the algorithm, you are already restricting the all the possible clean images that can fit this dirty image. So then you, by selecting this, the algorithm is only going to subtract clean images from here. So it will subtract these point sources with all their contributions, and the rest of the image is not touched. Yeah, but so you will see if you press clean. I'm going to. What is that? I think it's. It's not. I didn't put it in the slides. Okay, I'm going to put it now. So, yeah.
When they say also in the UV space, where's the UV space? The one?
Sorry. Can you go back to here? Show FTT.
Okay.
Going to. Yeah, so there was already a question on one of the exercises that tells you to put a clean box. I didn't explain that yet, so I'm going to explain it very briefly. So basically, in order to make your cleaning process faster, and what you do, because the solutions to our problems are infinite, we know. So you, as a physicist or as an astronomer, you are super clever, because, yeah, we don't have a learning machine yet, but there are already. So you are super clever, so you, in your dirty image, you select a region in which you are telling the algorithm only clean here, okay? So you are telling the algorithm, I believe, or I have reasons to think that most of the real signal and the brightest sources are in this region. So you select, it can be, here it's, I think it's squares, but in CASA you can choose shapes, okay? It doesn't need to be a square. But the thing is that you select a small region, and that helps the algorithm to clean faster and converge much better, and you also get less noise in the output. So in one of the exercises telling you put a box in one of the bright sources and do cleaning and see what's happening. And then it also tells you in the next step, add more boxes to other sources. So if you just select one single box and you are telling the algorithm clean only here, it's only going to apply the subtraction only that region, and the rest will be always in the residuals. There's no way you can take it out, because you have told the algorithm only take into account this region. So what we do usually, what you do first is you open your dirty image, you kind of see where the brightest sources are, you put cleaning boxes in there, and then you make the algorithm run for a bit, and you see how it works. And perhaps, depending on the sources that you are seeing, you need to make those boxes larger or smaller. The more precise the boxes are, the better you will be subtracting and defining a nice model. So this selection of boxes is just to help the algorithm to get a faster and nicer result. So it's in the exercises. And I think it's very easy in the window. You just, with the mouse, you select the region and then you press go. You had a question, right? Or was this related to?
That's a question. We have the clean image, okay?
Yes.
And we have the residuals, but we also see this like
Side lobes.
But I mean, maybe because we know how's the actual model, we can say okay, there's no more. But let's say we don't have it, so
Yeah, you don't know. Yeah, of course.
So what happened with this? How do we know we have to stop here? You know?
Yeah, this is related to what I was saying with the shape of the residuals. Here you see that it's not random noise. It has some. So it depends if you are looking for the dynamic range, and then you compare. I think you can do the scale.
I already.
That's already. So you can, if you compare like the brightest point here with the brightest point in the residuals.
This is the brightest point.
Yeah.
This is the brightest point of here. So
it's already, this is 8 to the minus 2, and this is
1.
1. So it's already quite a... quite a good... so if you knew the RMS, then you would keep cleaning deeper. Usually you go for it. You just keep cleaning until your noise has no artifacts. So
I can still clean.
huh?
So can I still clean or?
Yeah, did you stop because the iterations were 10 only?
No, I take 100. So
Okay.
First I made the 100,
And then 10 more, okay.
to see if there's
Yes.
any change.
Yeah, at some point, so because you are telling, it's also the drawback, because you are telling the algorithm, I believe, so I think I want to keep my model with with sources here, and there. Then you are having the drawback of
you usually know where's the
no, you don't know. When you are observing for the first time, you don't know. So you check the dirty image,
but maybe
and then you see the brightest point where it is, kind of, and then you make a region around it, and then you clean. And because the thing of the making the cleaning boxes, what is allowing you is to subtract the brightest contribution, and then you can see what's in there left. Because otherwise, if you have something super bright and you start cleaning and making cleaning components, you you can see clearly what's behind. And so taking the brightest components out, it allows you to see what's left there. And then perhaps you can say, oh, this might be real, this might not, but this can kind of look a bit of like the pattern of my dirty beam. So they don't look like I have something else more, right? So you select the boxes, and then you basically then look at the residuals and see if they are Gaussian or. And then here I think.
So where is the U? So where
This
will
is
be
the
the
dirty
dirt?
beam.
And here in this plot, where I should be this.
This is this, right? And this is the Fourier transform of your clean model. And this is the.
And the residuals. So
No, but this is I think this is only from.
But-
you can read in the-
so I have to get the dirty beam close to the residuals, or no? Similars, or no?
if you want to get the dirty beam,
Yeah, if I already did the cleaning algorithm in the right
Yes.
way, my residuals, the Fourier transform, should be like the dirty beam, or not?
no, if you have subtracted up to the noise level, then they will probably don't have residuals that have show the pattern of the dirty beam. So yeah, perhaps that means that you can clean a bit deeper. Okay.
It's the same pattern.
So it's something that once you are below the noise and you can see that you get the beam pattern in the noise, that's what you can get. You cannot get anything else. So it doesn't look like you have extra sources there. I mean, you chose because you know it, right? But if you didn't know, I
can say, okay, I made 100 iterations more, and
I'm already below the noise, and the only residuals that I see there are compatible with the beam pattern at the noise level. So they are just there's nothing else. But usually, if you have like a very bright source, especially in the outer parts of the image, this is very if you have such a source there, because you have the beam pattern, the side lobes of a bright source go into the center of the image. I don't know if you have here. No, this is the other one.
We didn't make it.
Sorry.
Robust.
What's your beam size here? No, it's not there. It's not showing the. Perhaps because you are already doing something else. But so the beam pattern has a response like this, okay? In the center of the image, you are super sensitive, then you lose sensitivity, but then you have like a tail. So the sources that are not in the center of the image, but are in that area, are in the side lobe. If they are very bright, the flux goes into the center of the image as well. So if you have a bright source in one of the edges of the image, and you put a cleaning box there, when it's subtracted, you immediately, all of a sudden, you are able to see what's in the middle of the image. So that's why clean boxes are very useful, especially if you have bright sources that are not in the center. Because then when it subtracts the brightest, all of a sudden you unveil what was in the middle that you couldn't see because you had the side lobes of this super very bright source that was more in the outside. Here you have nothing in the center because there's no point source, there is no source in the middle. But imagine that you had only this bright source and an extended source here in the center. I don't know if there is one model like this.
Yeah, like the galaxies.
I think when you have the dirty image, you have like a super bright source there, and then kind of a weird pattern, and almost and you can see nothing in the center. So what you do is you select first this bright source, and then you clean, and then all of a sudden, you can easily see in the next iterations that you have many more clean signal in the center that you couldn't see before. Whereas if you don't make this small clean box, it's going to get rid of that bright source, but we have the gain, so you are not subtracting all of it. So you will still have other secondary ripples, perhaps, of this super bright source, that in the next iteration, there will be the next thing that the algorithm will try to clean. And that's not a real source. It's just the secondary lobe of a very bright source. So if you just put a small box around a very bright source, in the next iteration you can start already to discern other bright sources and put more boxes there.
I'm sorry, I missed that part. When I'm doing the clean algorithm, the clean algorithm tries to fit to a Gaussian in order to get the
so the clean algorithm does. So ideally, you